Okay, hey folks, we are going to take what we discussed, this whole notion of state functions having exact differential expressions, and apply it to du. And in doing that, we're going to see what type of derivatives manifest, and if those derivatives have physical implications, like are they things that we can observe in nature. So we want to come up with an expression for du, and for now we're going to say constant number of n, so closed system, that will express our state function and its infinitesimally small changes. And for now we're going to choose T and V, but we'll see what happens when we put pressure in the mix. So we'll say U is a function of temperature, volume, and pressure, and we'll just look at those changes in temperature and volume. So we can start by saying du, the total differential expression in U, is the following. It is the partial of U with respect to V at constant T dV. And because this is a state function, we can now change the order of that differentiation. So partial of U with respect to temperature at constant volume times d temperature, right? And we multiply it by the respective variable so that our units will work. Okay? So now we'll play this game where we inspect these derivatives to look for things that are physically observable. And hopefully what we can see right away, the partial of U with respect to the partial of T at constant V is CV. So that's pretty cool. So we can now rewrite this expression with that in place. Okay, so we're going to replace that partial with now just CV dt. And now what we want to do is look at this derivative and see if there's anything that we can make sense out of from it. So the first thing we'll do is look at the units. Okay, so if we look at those units, we can see that's going to be a joule per meter cubed. So recall a joule is a kilogram meter squared per second squared, and then divided by a meter cubed. That all gives us a kilogram per meter second squared, which is the exact same thing as a Pascal. So this derivative has units of pressure. And as it were, we call this the internal pressure because it manifests from changes in the internal energy. So what is this quantity and how can we measure it? So this quantity, internal pressure, gets the symbol pi sub t. So now we can rewrite our differential expression in U in a simpler way. We can say that du equals pi t dv plus cv dt. And now we're going to play with this pi t a little bit more and think about what this is. So in the Joule experiment, James Joule sought out to measure pi t with the following experiment. So we had a large water bath, and in that water bath were submerged two chambers, one being at high pressure and one being at vacuum, and a thermometer inside. And when Joule opened up these chambers, the high pressure side expanded out into vacuum, right? So from its V initial to its V final. And what Joule was hoping to see was if there was any type of heat exchange or work being done that he would be able to measure that through the change in temperature. Well, as it turns out, there was no temperature change here. So we can kind of conclude several things from this. So if there's no temperature change, then automatically we have to say that there was no change in internal energy for the following arguments. We know delta U is Q plus W. We now know when something expands into vacuum, there's no work being done. And if there was no temperature change, then Q also had to be 0. So thus he concluded no temperature change means no change in internal energy, which means for an ideal gas, pi t must be equal to 0. Which is one of our pillars of the ideal gas law, right? There are no interactions between gas molecules, so if we separate them or compress them, there should be no heat exchange. Well, we now know through the van der Waals equation, it can be proven, and I'm not going to do this for you explicitly, but we can show that pi t for a van der Waals gas equals A over Vm squared. So it contains that A coefficient that describes our interaction of gases, which is pretty cool. And if we think about a plot of this, what it would look like. So remember, this pi t equals partial of u with partial of v at constant t. So if we have a graph of u versus v, the slopes of those behaviors will give us this internal pressure. So a perfect gas has a slope of 0, right? So if we look out to really large volumes where our gas molecules are separated away from each other, that will be real gas behavior, or ideal gas behavior, rather. However, if we look at the two different considerations here, so consideration number 1, where pi t is a positive quantity. So in other words, the slope of this line is positive. That shows that the internal energy of a gas increases as we spread them further out. And we can conclude that for that to be true, attractions must be dominant, because if we have to put energy in to our gases to get them to separate, that means they were attracted to each other. Okay, conversely, when this slope is negative, repulsions are dominant. And we know that that must be true because if the internal energy decreases, or in other words, if energy is released as a result of these gases expanding, that means they weren't very happy being close to each other, and they released energy as a result of expanding. Okay? So this is all good for gases. So what if we want to consider other systems, other phases, for example? Well, we can now start to go back and play with our differential expression once again. So let's look at that. Partial of u with respect to v at constant t dv plus the partial of u with respect to, oops, I wrote p, but I meant to say t. Okay, partial of u with respect to the partial of t at constant v dt. So now we can write, I'll just get rid of those derivatives really quickly by writing pi t dv plus cv dt. So now what if we want to look at how the total internal energy changes with changes in pressure at constant temperature? Okay. Well, so that would still equal pi t, but now we'd be looking at changes in volume with respect to changes in pressure at constant temperature. Okay, great. And then we still have this CV term, dt, so now that's going to be changes in temperature with respect to changes in pressure at constant temperature. Well, if it's constant temperature, that's going to all drop out. So now we just have this thing to consider, changes in volume with respect to changes in pressure at constant temperature. And through some unit analysis manipulation and including a negative sign to be consistent with how we view exothermic and endothermic, we note that we can describe that as what's referred to as the isothermal compressibility. So how the volume of a sample changes as we change its pressure. Similarly, we can look at the total du, total changes in internal energy with respect to changes in temperature at constant pressure. And so we still have pi t, but now that's going to give us the derivative dv by dp at constant t and we still have CV here. And now that's going to be partial of T over the partial of T at constant P, so that term also drops out. And now we can see here, if we consider how the, I knew I was going to get that confused. It's so easy to confuse those. Partial of V with respect to T at constant P. So now we can see as the volume of a sample changes with respect to changes in temperature, we refer to that as the expansion coefficient. Okay. So as we can see right here, here's some sample values. And the way that these values work, the larger that these quantities are, the more a sample responds to that change. So for example, benzene has a really large isothermal compressibility coefficient. So that means it is very compressible. It will change volume enormously with changes in pressure. Similarly, you can see the alpha constant for benzene is also large compared to those in this list. And what that means is the volume of a sample of benzene is quite responsive to changes in temperature. So a sample of benzene will expand enormously when subjected to great changes in temperature. And if we now compare that to something like diamond, diamond has both a very small isothermal compressibility and a very small expansion coefficient, meaning diamond will not expand by very much when we heat it up, nor will it compress when we add a lot of pressure to it. Okay, so we'll go through some more sample calculations and talk about how we can apply this partial derivative relationship into something more useful for measurable quantities in our live lecture. I'll see you then.